Each meter base and its associated fuse main disconnect should have its own separate cold water ground and building steel ground. The equipment grounding conductor, or EG, from the service trough should be connected to each meter base's neutral bar. There are several reasons why separate grounds are important. Firstly, it protects against ground faults. Separate grounds provide multiple paths for fault currents to flow, reducing the risk of electrical fires and shock hazards. Secondly, it ensures proper bonding. Bonding the disconnect neutral bar to the trough ground and ground rod ensures that the equipment is properly grounded in case of a ground fault. Thirdly, it complies with codes. National Electrical Code, or NEC, Article 250.32 requires that all service equipment and metal enclosures be bonded to the grounding electrode system. The current installation method of grounding some disconnects through the trough and others separately is incorrect and can create issues. One such issue is unequal grounding. Disconnects grounded through the trough may have different grounding impedances than those grounded separately, reducing the effectiveness of the grounding system. Another potential issue is voltage imbalances. If the trough grounding is not properly sized, it could introduce voltage imbalances into the system. Finally, the current installation method may not comply with NEC requirements for proper grounding, leading to code violations. To ensure proper grounding, the following corrective actions should be taken. Firstly, install a separate cold water ground and building steel ground for each meter base and disconnect. Secondly, connect the EGC from the service trough to the neutral bar of each meter base. Thirdly, bond the disconnected closure to the neutral bar and ground rod using a separate EGC. It is also important to verify that all grounding connections are secure and have proper continuity to ensure their effectiveness and safety. The purpose of an equipment grounding conductor, or EG, is to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protection devices such as circuit breakers and fuses to quickly clear the fault and minimize the risk of electrical shock or fire. The size of the EGC is determined by NEC Table 250.122 and is based on the size of the overcurrent protection device protecting the circuit. The grounding electrode conductor, or GEC, connects the equipment grounding system to the grounding electrode system. The grounding electrode system typically consists of a metal underground water pipe, a building steel frame, and/or ground rods or ground rings. The GEC provides a path for fault current to flow to the earth, helping to stabilize the voltage to ground and further reduce the risk of electrical shock. The size of the GEC is determined by NEC Table 250.66 and is based on the size of the service entrance conductors. Bonding refers to the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Proper bonding reduces the impedance of the ground fault current path and provides the capacity to carry the current safely. Bonding is essential in electrical systems to minimize voltage differences between metallic parts, which could create a shock hazard. There are several types of bonding, including equipment bonding, which connects non-current carrying metal parts of equipment together, and main bonding, which connects the service equipment to the grounding electrode system. The NEC provides detailed requirements for bonding in Article 250. A ground fault is an unintentional electrical connection between a live conductor and ground or a grounded metal part. Ground faults can occur due to damaged insulation, loose connections, or equipment failure. When a ground fault occurs, current flows through the unintended path to ground, which can create a shock hazard or cause a fire. Ground fault circuit interrupters, or GFCIs, are designed to detect ground faults and quickly interrupt the circuit, minimizing the risk of electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, to protect people from ground faults. Proper grounding and bonding are essential for preventing ground faults and ensuring electrical safety. The National Electrical Code, or NEC, is a comprehensive set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC is updated every 3 years and provides detailed requirements for grounding, bonding, wiring methods, overcurrent protection, and other aspects of electrical installations. Compliance with the NEC is essential for ensuring the safety of people and property. The NEC is adopted by many state and local jurisdictions and is enforced by electrical inspectors. It is important for electricians, electrical contractors, and other professionals to be familiar with the NEC requirements and to follow them carefully when designing and installing electrical systems. Article 250 of the NEC covers grounding and bonding requirements. This article provides detailed rules for grounding electrode systems, equipment grounding conductors, bonding conductors, and other aspects of grounding and bonding. It is important to follow the requirements of Article 250 to ensure that electrical systems are properly grounded and bonded. The NEC also includes requirements for specific types of equipment and installations, such as swimming pools, healthcare facilities, and industrial locations. These requirements are designed to address the unique hazards associated with these types of installations. Regular inspections and maintenance of electrical systems are essential for ensuring the continued safety and reliability. Inspections can identify potential problems such as loose connections, damaged insulation, and overloaded circuits. Maintenance can address these problems before they lead to more serious issues such as electrical fires or equipment failures. It is important to have electrical systems inspected and maintained by qualified professionals. The use of appropriate safety equipment is also essential when working on electrical systems. This equipment includes rubber gloves, insulated tools, and safety glasses. These tools help protect workers from electrical shock and other hazards. It is also important to follow lockout-tagout procedures when working on electrical equipment to prevent accidental energization. Proper training is essential for anyone working on electrical systems. Training should cover the NEC requirements, safe work practices, and the use of safety equipment. It is also important to stay up to date on the latest electrical technologies and best practices. By following these guidelines, it is possible to ensure the safety and reliability of electrical systems. Grounding electrode conductors are sized according to NEC Table 250.66, based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 or American wire gauge copper, the grounding electrode conductor would typically be no smaller than number 2 American wire gauge copper. However, there are exceptions to this rule, such as when the grounding electrode conductor is connected to a concrete encased electrode or a ground ring. In these cases, the grounding electrode conductor is only required to be number 4 American wire gauge copper. It is important to consult NEC Table 250.66 and the applicable exceptions to determine the correct size of the grounding electrode conductor for a particular installation. Equipment grounding conductors are sized according to NEC Table 250.122, based on the size of the overcurrent protection device protecting the circuit. For example, if the overcurrent protection device is rated at 20 amps, the equipment grounding conductor would typically be no smaller than number 12 American wire gauge copper. If the overcurrent protection device is rated at 60 amps, the equipment grounding conductor would typically be no smaller than number 10 American wire gauge copper. It is important to consult NEC Table 250.122 to determine the correct size of the equipment grounding conductor for a particular circuit. Bonding jumpers are used to connect metallic parts together to ensure electrical continuity. Bonding jumpers are sized according to NEC 250.102, which requires them to be sized based on the size of the equipment grounding conductor for the circuit. For example, if the equipment grounding conductor is number 10 American wire gauge copper, the bonding jumper would typically be no smaller than number 10 American wire gauge copper. It is important to ensure that bonding jumpers are properly sized and installed to provide a low impedance path for fault current. The grounding electrode system is the connection to earth. This can include a metal underground water pipe, the building steel, a ground ring, or ground rods. The grounding electrode system is used to stabilize the voltage to ground and provide a path for fault current to flow to the earth. The NEC provides detailed requirements for grounding electrode systems in Article 250. It is important to follow these requirements to ensure that the grounding electrode system is properly installed and effective. A metal underground water pipe, when used as a grounding electrode, must be supplemented by an additional electrode, such as a ground rod or a ground ring. This is to ensure that the grounding electrode system is effective even if the water pipe is disconnected or becomes non-conductive. The supplemental electrode must be bonded to the water pipe with a bonding damper. Building steel can be used as a grounding electrode if it is effectively grounded. This means that the building steel must be connected to the earth with a low impedance connection. The connection can be made to a metal underground water pipe, a ground ring, or ground rods. A ground ring is a bare copper conductor that is buried in the earth around the perimeter of a building. The ground ring must be at least 20 feet long and must be buried at least 2.5 feet below the surface. Ground rods are metal rods that are driven into the earth. Ground rods must be at least 8 feet long and must be driven into the earth until at least 8 feet of the rod is in contact with the soil. 2 or more ground rods must be installed at least 6 feet apart. The resistance to ground of the grounding electrode system should be as low as possible. The NEC requires that the resistance to ground not exceed 25 ohms. If the resistance to ground exceeds 25 ohms, an additional grounding electrode must be installed. The resistance to ground can be measured with a ground resistance tester. This tester applies a current to the grounding electrode system and measures the voltage drop. The resistance to ground is calculated using Ohm's law, which states that resistance is equal to voltage divided by current. It is important to measure the resistance to ground of the grounding electrode system periodically to ensure that it is still effective. The NEC requires that the grounding electrode system be inspected and tested annually. In addition to the grounding electrode system, other metallic parts of the electrical system must also be bonded to ground. This includes metal conduits, metal enclosures, and metal equipment. Bonding ensures that these metallic parts are at the same potential as ground, which reduces the risk of electrical shock. Bonding is typically accomplished by connecting the metallic parts to the equipment grounding conductor. The equipment grounding conductor is a conductor that runs with the circuit conductors and is connected to the grounding electrode system. The equipment grounding conductor provides a lower impedance path for fault current to flow back to the source. It is important to ensure that all metallic parts of the electrical system are properly bonded to ground. This will help to protect people from electrical shock and prevent damage to equipment. Ground fault circuit interrupters are devices that are designed to protect people from electrical shock. GFCIs detect small amounts of current leakage to ground and quickly interrupt the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. GFCIs are very effective at preventing electrical shock. However, they are not a substitute for proper grounding and bonding. It is important to have a properly grounded and bonded electrical system, even if GFCIs are installed. Arc fault circuit interrupters are devices that are designed to protect against electrical fires. ASIs detect arc faults, which are dangerous electrical discharges that can cause fires. ASIs are required in many locations, such as bedrooms. ASIs are very effective at preventing electrical fires. However, they are not a substitute for proper wiring and installation. It is important to have a properly wired and installed electrical system, even if ASIs are installed. Surge protective devices are devices that are designed to protect against voltage surges. Voltage surges are sudden increases in voltage that can damage electronic equipment. SPD are installed at the service entrance and at sensitive equipment. SPD are very effective at protecting against voltage surges. However, they are not a substitute for proper grounding and bonding. It is important to have a properly grounded and bonded electrical system, even if SPD are installed. Proper grounding and bonding are essential for electrical safety. By following the NEC requirements and using appropriate safety equipment, it is possible to ensure the safety and reliability of electrical systems. When dealing with multiple buildings or structures supplied from a single service, it's crucial to understand the grounding and bonding requirements outlined in the NEC. Generally, each building or structure is required to have its own grounding electrode system. This ensures that each building has its own reference to ground, minimizing potential differences and improving safety. The grounding electrode system for a separate building or structure can consist of various components, such as a metal underground water pipe, a building steel frame, a ground ring, or ground rods. The specific requirements for the grounding electrode system depend on the size and type of the building or structure. The equipment grounding conductors that run between the buildings or structures must be sized according to NEC Table 250.122. These conductors provide a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protection devices. In addition to the grounding electrode system, each building or structure must also have its own main bonding jumper. The main bonding jumper connects the grounded conductor, typically the neutral, to the equipment grounding system of the service equipment. This connection ensures that all metallic parts of the electrical system are at the same potential as ground. The size of the main bonding jumper is determined by NEC Table 250.66. It is important to note that the grounded conductor should only be connected to the equipment grounding system at one point, typically at the service equipment. Connecting the grounded conductor to the equipment grounding system at multiple points can create circulating currents, which can be a safety hazard. When dealing with interconnected electrical systems, it's crucial to ensure that all grounding and bonding connections are properly made. This includes checking the tightness of all connections and verifying the continuity of the grounding and bonding conductors. Regular inspections and maintenance of the grounding and bonding system are essential for ensuring its continued effectiveness. If any problems are found, they should be corrected immediately by a qualified electrician. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements and best practices, it's possible to minimize the risk of electrical shock, fire, and equipment damage. In cases where there are multiple services in a single building, each service must have its own grounding electrode system. The grounding electrode systems for the different services must be bonded together to create a common grounding system. This bonding helps to equalize the potential between the different services and minimize the risk of electrical shock. The bonding conductor that connects the different grounding electrode systems must be sized according to NEC Table 250.66. It's important to ensure that the bonding conductor is properly installed and that all connections are tight. In addition to the grounding electrode systems, all metallic parts of the electrical system must be bonded together. This includes metal conduits, metal enclosures, and metal equipment. Bonding ensures that these metallic parts are at the same potential as ground, which reduces the risk of electrical shock. The bonding conductors must be sized according to NEC 250.102. It's important to ensure that the bonding conductors are properly installed and that all connections are tight. Regular inspections and maintenance of the grounding and bonding system are essential for ensuring its continued effectiveness. If any problems are found, they should be corrected immediately by a qualified electrician. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements and best practices, it's possible to minimize the risk of electrical shock, fire, and equipment damage.